In this video, we're going to go through topic 5, section 5, which is titled Logarithmic Functions. So in this section, we're going to do two different things, one of which is graphing logarithmic functions, and then the other one is finding the inverse of exponential and logarithmic functions. So we already looked at finding the inverse of a very basic exponential function. So we're going to add some steps to that process from what we did on the last lesson, as well as looking at some graphs. So in Math 1, you learned how to graph exponential functions. And so with exponential functions, you used a table of values that went from -2 to +2. And you plug those values into the exponent, and you drew a graph that, remember, never crossed the x-axis. And so in Math 3, when we did rational functions, we talked about asymptotes. And so what really is happening is that an exponential function has an asymptote on the x-axis if there's no transformations. And so we're going to look at a log function, which is the inverse of a exponential function. So their graphs are reflections across the line with the equation y equals x. So that line that's highlighted in the diagram, the dotted line, is the line of reflection between the red y equals 10x and the blue y equals log. Remember, there's no base there, so that implies that it's a base 10. That's the common log. We will work with some transformations. And so the transformational form of a log equation is y equals a times log of base b of the quantity x minus h plus k. Remember that h and k translate the graph, h horizontally, left to right, and k vertically, up or down. Remember that when we identify h, because of that x minus h, the number inside is the opposite of what h really is. So a positive h moves it to the right, a negative h moves it to the left, and then plus k moves it up or down. So positive up, negative down. Remember that if a is negative, that means it's a reflection across the x-axis, and it creates a vertical stretch if that number is something that is larger than 1, or a compression if it's a fraction, so something smaller than 1, a proper fraction, that is. So for the first example, we're going to graph a basic log function using the inverse. So what we're going to do is, the idea of inverse is that x and y switch. So we know how to calculate 2 to the x power. So we're going to use that to help us graph log base 2 of x. So if we think about 2 to the x power and we have these x values, we're going to do 2 to the -2 power. Remember, that's the same as having 1/2 squared. And so if I square 1/2, that's 1/4. So that means that the y value at -2 is positive 1/4. If I raise 2 to the -1 power, that's the same as having 1/2 raised to the positive 1 power, which is just 1/2. If I raise 2 to the 0 power, remember, anything to the 0 power is just 1. So I don't really need to simplify anything there. 2 to the first power is 2, and then 2 squared is 4. So I get this table of values for y equals 2 to the x power. Since log base 2 of x is the inverse of that, and again, we learned that in the last lesson, all I have to do is interchange the x and y values to represent y equals log base 2 of x. So notice that since the x's were already filled in, I filled in the y's for you. So we're just putting our y answers in for x here to create that inverse. So I'm going to graph as a dotted line this one, just so that you can kind of see what the exponential graph looks like, and a reminder to you about how that worked, and we'll talk about the asymptote as well. So if I plot the point -2, 1/4, that's kind of close to the x-axis here. -1, positive 1/2, 0, 1, 1, 2, and 2, 4. So this dotted line would represent the exponential graph y equals 2 to the x. So this graph would have an asymptote at y equals 0. So that x-axis would be the asymptote for that graph of 2 to the x power. So I'm going to draw in that dotted line of y equals x. We'll highlight in that line. So y equals x is the diagonal line going through the corners of the graph. So that's going to be the line of reflection. So what that means is that when I actually plot the graph for this one, and I'm going to graph this one in blue just so it stands out a little bit better, and I'm not going to do it dotted. So now my x value is 1/4. So my x value is super close to the y-axis, and my y value is -2. And then at positive 1/2, I'm at -1. At 1, 0, 2, 1, and 4, 2. So notice that I have that same curved shape. And so this one, if I think about what would happen over here, is that this pattern would continue and I would get something like 1/8, right? If I use -3, I would get 1/16, I would get 1/32. So these values are never going to become 0, but they're getting very, very, very close. And so what ends up happening then is that this graph, and I'm going to draw the asymptote as a solid line just so we can kind of see it there, has an asymptote at x equals 0. So if we think about what happens when I'm graphing an inverse, I switch everything to x and y. So the original asymptote was at y equals 0. If I switch x and y, that becomes x equals 0. So the blue and orange graph represents the graph of log base 2 of x. If I think about the domain, the x values, since there's an asymptote at 0, are never going to be on this side of the graph. So that means that the domain of this graph goes from all x values that are greater than 0, because it's on that right-hand side. If you prefer interval notation, you can write that as, remember, the 0 would have a parenthesis because I don't have an equal sign here. So from 0 to infinity. Okay, so the domain values, all the x's that will work, are really, really small fractions up until infinity. If I think about the range of this graph, so if I look at the values from bottom to top, this is increasing at a slower rate at the top, but it is increasing forever. So that means that the range is actually all real numbers. Remember that the interval way to write that is from -infinity to +infinity. If we look at the graph is crossing the x-axis at 1. So the x-intercept is at the point 1, 0. End behavior. So when we looked at end behavior with other graphs, we talked about it as, and I'm going to fill this in, so don't copy this yet, from -infinity to +infinity. However, with graphs with asymptotes, if they're vertical asymptotes like this, the one of the end behaviors is going to change to whatever that asymptote value is. So if I look at the left side of my graph, there's nothing over here right, because -infinity implies I'm looking in this direction. There's nothing over there. And so what ends up happening is that the value on the left in my end behavior, I'm actually looking at what happens, not when it approaches -infinity, but when it approaches 0. So as my graph approaches 0, it's pointing down. And so since it's pointing down, that means that the function is approaching -infinity. Okay, so remember that means that the arrow is pointing down on that side. On the right, if I look at my graph, it's technically increasing, right? It's pointing up over here, so that means that this one's going to be +infinity. So the left side of my graph is pointing down. However, it's not at -infinity, it's at the value of the asymptote, which was 0. Okay, so that is the graph of a logarithmic function. What we're going to look at in example 2 is what happens when I now do transformations on that logarithmic function. So for this first problem, for this next problem, we have g of x equals negative log base 2 of x plus 3 plus 1. And so we're going to talk about how the asymptote and x-intercept of the given functions compare to the parent function. So the parent function is the function y equals log base 2 of x, which is in example 1. So when I'm thinking about the parent function, I'm just going to copy this table from above. We just went through this process. So this is still that same function that we just graphed that has the x values 1/4, 1/2, 1, 2, 4. So I'm literally just copying this because if I look at the base of the function, the base is 2, and so that's where the parent function comes from. So it's just log base 2 of x. So if I'm identifying the transformations, I want to think about what is a, what is h, what is k, and how do those translate our graph. So remember that a is the number that's in front of the log. Since it's just a negative sign, that means that a is -1. Remember that that means that this is a reflection across the x-axis. There are no stretches or compressions because it's 1, right? So a stretch happens if it's greater than 1. A compression happens if it's smaller than 1. So if it was 2, it would be a vertical stretch by 2. If it was a 1/2, it would be a vertical compression by 2. And so h is the number that's being subtracted from x. In this case, it's being added, so that means that h is -3. So that means that our first translation is going to be left 3. And then a k is the value that is being added or subtracted on the outside, so that means that k is 1. And so since it's positive, it's going to go up 1. So the graph g of x equals negative log base 2 of the quantity x plus 3 plus 1 is going to be the graph of the parent function reflected across the x-axis and then translated left 3 up 1. So in the original, we had an x-intercept at 1, 0, and an asymptote at x equals 0. So we're going to look at some relationships here for this problem. So for the graph, let's start by just plotting these points. So I'm not going to connect them because this is going to be the parent function, but I need those points in order to draw my transformations. So I'm going to start with these points. So I have 1/4, -2, 1/2, -1, 1, 0, 2, 1, and 4, 2. So I'm going to switch colors for each of these steps, and I'm going to make them kind of match what was here. So I'm going to do red points where I reflect these points across the x-axis. So if the x-axis is horizontal, that means I'm reflecting them this way. So since this is 2 above the x-axis, a reflection is going to be 2 down. If you don't have different colors, what you could do is just use like an X to show that. So I'll do that as well. So I reflect this over the x-axis. It's there. Since this point is on the x-axis, reflecting it still stays on the x-axis. Then I'm going to reflect this point. So it's at 1/2. It was 1 below, so now it's 1 above. And then this one was 2 below, so now it's 2 above. So my reflected graph is this shape here. I'm going to leave that as points though, just so we can see the process of the work. And then for my final graph, and I'm just going to use blue because that's the first color, but I'm going to do both translations at the same time. So I'm going to translate left 3 up 1. So starting on the right, I'm going to go left 3 up 1. So my point is there, left 3 up 1. So I'm at -1, 0. Left 3 up 1. So I'm at -2, 1. Remember, this is a half. So if I go left 3, I'm at negative 2.5 up 1. And then this is a quarter. So if I go left 3, I'm at negative 2 3/4 up 1. So remember that on this side, it's increasing. On this side, it's just going to become smaller and smaller fractions. So whatever the closest line is in that direction, that's going to be the value of the asymptote. So if I look at where the asymptote's going to lie here, the asymptote is going to be at negative 3. So the asymptote here is x equals negative 3. If we look at our graph, the x-intercept is at negative 1, 0. So what you should notice is that that negative 3 appeared in our equation. So the negative 3 was our h value. That's where our asymptote ends up. And so that will always be the case. So if I am needing to find the asymptote of a graph and I just have the equation, I can find that by looking at the h value in the equation to tell me the location of the asymptote as an x equals equation. So then for your homework, a lot of them are just asking you to identify the transformations and to talk about that relationship. I believe that when you're graphing, you're just graphing the ones that are the parent functions. So then let's look at example 3, and we have quite a few of these just because the processes can be a little bit different depending on how many steps we were given. And so for all of these, I wrote generic steps down. So what is the inverse of what is the equation of the inverse of the function? So we have 3 different functions. 2 of them are exponential, so I have a base 10 and a base e, and then 1 is logarithmic. And so for each of these problems, because they are inverse problems, remember that the main idea of finding the inverse is switching x and y. So our first step is if we're given function notation here, so we're going to change the name, and I just wrote f of x. There's a g and an h, but either way, we want to take the function notation and rewrite that as a y, because our next step is to switch x and y. And so then what will happen in some of the problems is that we want the log or the base with the exponent to be isolated. It's okay for more things to be in the exponent or inside the parentheses. So for example, in B, see how it's x plus 5 in parentheses. That's okay. I was just using the y kind of generically. I guess I could put like no, that's fine. And we're going to do that using inverse operations. Step 3 really only is going to happen in problem C because the base is not isolated at this point. Then we're going to go ahead and switch forms. So if I have a log equation, I'm going to change it to an exponent. If I have an exponential equation, I'm going to change it to a log. And then finally, we're going to continue to solve for y using inverse operations. And then that will give us the inverse function. So if you need to pause that to write those down, it might be a good idea to do that now. So for the first step, we're going to rewrite f of x as y. So I'm going to take this and I'm going to write y equals 10 to the x plus 1. And then within that, I'm going to switch the locations of x and y. So that means I'm going to change it to be x equals 10 to the y plus 1. So for this case, it wants me to isolate the base with the exponent, which is happening, right? So I have that isolated. There's nothing outside of that box that contains the base and its exponent. So that means that I don't need to do step 3, but I do need to, then I can go on to step 4. So this is the only step 3, that's technically optional. So when I'm changing forms, I start at the base, and remember we go to the other side of the equal sign. So that means that we've got log base 10 of x, and that is equal to from the x, I'm going to the other side of the equal sign to what I have left over, which is y plus 1. So remember that because I have a log base 10, I can ignore that 10 because that is the common log. Okay? So what I really have here then is log of x equals y plus 1. And then my last step is to solve for y using inverse operations. So since I have y plus 1, I'm going to subtract 1 from both sides so that y is by itself. Notice that anything attached to the log, I'm not subtracting inside there, I'm subtracting it separately. So what this leaves me with is log of x minus 1 equals y. So what that means is that my inverse, remember that the notation for inverse is I take the function name and I use a negative 1 power, so f inverse of x is equal to log of x minus 1. So that is my answer for example 3a. So the inverse of 10 to the x plus 1 is log base 10 of x minus 1. Okay, so for the next one, we have a log function. So instead of isolating the b to the y power, we're going to be isolating log base b of y. Okay, so our first two steps are the same. Step 3 is the one that changes just based on what kind of function we were given. So remember that we're just changing that first part of this to y. So y equals log base 7 of x plus 5. And then we're going to take and switch x and y, or interchange x and y. So I have log base 7. I'm going to change my y to an x and my x to a y. So that gives us x equals log base 7 of y plus 5. On the right-hand side, because everything that's not the log is inside parentheses, I have this isolated. So I do not have to do any work for step 3. Step 3 is good. I'm ready to change forms. So to change forms, I'm starting with the base. So the base of the log is 7. And I'm going to go to the other side of the equal sign. So that's going to give us 7 to the x. And then from the x, I'm going to the other side of the equal sign again, equals y plus 5. So 7 to the x power equals y plus 5. In order to get at y by itself now for step 5, I'm going to subtract 5 from both sides. Again, because that exponent is on the 7, I cannot subtract 7 minus 5 and get 2 to the x. This stays as 7x minus 5. These are not like terms. So that means that my inverse is g inverse, because this was a function named g. I'm going to write that a little bit smaller. So g inverse of x is 7 to the x minus 5. Okay, so in this last example, we will actually do something for step 3. So step 1 is that we change the function name to y. So in this case, h of x, we're changing it to y. So y equals e to the x minus 2 power plus 3. So think about this as though this one has an h, it has something with the x, and a k, it has something with outside of the exponent. So in the next step, we're going to switch x and y. I'm going to copy down everything besides x and y. So instead of being y equals, it's going to be x equals e to the y minus 2 plus 3. So in step 3, since this is an exponential function, we're trying to isolate b to the y power. So in this case, e to the y minus 2 is the base. So that 3 is not a part of the exponent in the problem. So what we have to do then is get rid of that 3 And so I want to use the opposite and subtract 3 from both sides in order to isolate that exponent and base. So that means that we get x minus 3 equals e to the y minus 2. So note that, like, if I had, for example, 5 times e to the y minus 2 plus 3, I would have to subtract the 3 from both sides. And then I would have to divide both sides by 5. So you might have to do more than one of these inverse operations in at least one of the assignment problems. Okay, so now that I have the e to the y minus 2 isolated, so I have what I need, that's all that's on one side, then I can change forms. So since I have a base of e, I'm going to start there. So I'm going to do log base e of x minus 3 equals the exponent y minus 2. So remember that log base e is the natural log. So that means that this is really ln of x minus 3 equals y minus 2. So don't forget to simplify the natural log or the common log. And then finally, to isolate y, we have to add the 2 to both sides. Again, that 2 is not inside an ln of x minus 3, so I cannot actually add those two things together. These are not like terms, so we have ln of x minus 3 plus 2 is equal to y. So since our original function was h of x, that means that our inverse is h inverse of x equals ln of x minus 3 inside parentheses plus 2 outside of the parentheses. Okay, so those are the steps for finding the inverse of a more complicated log function or exponential function. Remember that when we did this in the last lesson, we literally just did step 1. Or sorry, we didn't have to do step 1. It was step 2 and step 4 only. Okay, so the more complicated the equation is that's given, the longer our steps are to find the inverse of the function.